In this segment, we focus on practical diagnostic methods within Azure's networking ecosystem. Having established how to create and configure virtual networks, subnets, and virtual network peering, we now delve deeper into identifying and resolving connectivity issues that may arise in complex scenarios. Troubleshooting network connectivity involves understanding the interplay among network security groups, NSGs, routing tables, public IP addresses, and other Azure components. By analyzing these elements, administrators can pinpoint potential misconfigurations or unexpected behavior. It is important to recognize that a single misconfiguration in an NSG rule or an incorrect user-defined route can disrupt connectivity from multiple resources. Azure provides several built-in tools to streamline detection and correction of these issues, ensuring environments remain both secure and accessible. This approach builds on preceding lessons to provide a structured template for analyzing, isolating, and ultimately fixing problems that might appear within Azure's distributed network architecture. Despite careful planning, virtual networks may experience unforeseeable disruptions. Typical connectivity issues arise from misconfigured subnets, improper inbound or outbound security rules, or conflicting user-defined routes. Occasionally, an organization might inadvertently set overlapping IP addresses within peered virtual networks, leading to routing conflicts and traffic restrictions. Clients may also experience connectivity challenges caused by DNS misalignment, either by using incorrect DNS servers or incomplete DNS record entries. In addition, a mismatch between allocated public IP addresses and internal naming structures can trigger accessibility limitations, especially for services that rely on inbound internet traffic. Over time, changes in firewall settings or updates to the NSG can generate disruptions that administrators must address. This wide array of potential issues highlights the importance of thorough network design and continuous monitoring. A well-implemented troubleshooting framework allows for methodical testing, helping to swiftly isolate and mitigate the root causes of connectivity problems. Azure offers a comprehensive suite of diagnostic utilities designed to accelerate resolution times for connectivity issues. These tools help administrators monitor data flow, validate routes, and detect anomalies throughout the environment. Among the available features are Network Watcher, IP Flow Verify, Packet Capture, and Connection Monitor. Each tool specializes in analyzing a specific aspect of network traffic, providing deeper insight into whether packets are being allowed or blocked. By reviewing logs and analyzing traffic patterns, administrators can also confirm that public IP addresses are mapped correctly and examine how NSG rules influence network flow. When used in combination, these solutions foster a streamlined approach to problem solving, mitigating guesswork, and reducing the time spent isolating faulty configurations. Consequently, they support ongoing best practices, like segmenting virtual networks, implementing appropriate routing strategies, and establishing clear firewall policies to maintain seamless connectivity across Azure's infrastructure. Azure Network Watcher provides a holistic set of tracing and logging capabilities that illuminate packet flow across virtual networks. It simplifies the process of diagnosing connectivity by generating insights on how traffic is being routed, where it might be dropped, and whether specific endpoints are reachable. Administrators can use Network Watcher to run the Connection Troubleshoot feature, performing hop-by-hop analysis from a source to a destination. This real-time data helps identify traffic bottlenecks, such as an NSG rule blocking inbound requests or user-defined route that inadvertently redirects traffic away from its intended target. Additionally, Network Watcher can capture topology diagrams that visually depict the resources in a virtual network, outlining the relationships among subnets, NCs, and gateways. By leveraging these features, network administrators gain a deep understanding of system behavior, allowing them to address problems swiftly and confirm that newly implemented changes achieve the desired results. IP Flow Verify is a targeted component of Azure Network Watcher that zeroes in on whether traffic is permitted or denied between two specific points. Administrators provide a source IP, destination IP, and protocol TCP, or UDP to see how the Azure infrastructure handles the connection attempt. This tool checks network security groups, local routing tables, and system rules to determine if the configured settings allow traffic to pass or if it gets blocked at any stage. By focusing on discrete pairs of addresses, IP Flow Verify isolates potential misconfigurations without requiring lengthy traces of an entire traffic path. When combined with logs from NSGs or other monitoring tools, IP Flow Verify clarifies which rule or route is responsible for blocking or allowing data flow. As a result, it is especially beneficial when troubleshooting newly created subnets or adjusting default rules to accommodate novel deployment requirements. Packet capture is another feature of Azure Network Watcher that records network traffic to and from virtual machines for in-depth analysis. By collecting data packets in real time, it identifies where the network flow disruptions might occur, revealing errors and anomalies within the TCP/IP stack. This offering integrates with tools like Wireshark for detailed reporting, letting administrators inspect specific traffic patterns, evaluate session timeouts, and trace potential security threats. Packet capture sessions can be configured to filter based on specific IP addresses, protocols, or ports, reducing the volume of data analyzed. In practice, an administrator might run a short-lived packet capture session to observe the pattern of failed connection attempts to a virtual machine behind an Azure load balancer. These low-level insights enable administrators to resolve underlying misconfigurations related to user-defined routes, conflicting firewall rules, or even application-specific bugs lurking beyond the initial scope of infrastructure analysis. Connection Monitor extends beyond simple packet-level diagnostics by continuously checking and reporting on connectivity between designated endpoints. This cloud-native solution tracks whether network paths remain reliable over time and collects vital performance metrics, such as latency or packet loss rates. By scheduling periodic tests, administrators gain a historical perspective on how network behavior evolves, enabling them to detect short-lived outages or degradations in service. Connection Monitor offers flexible deployment options that integrate with various Azure regions, affording a broader view of how geographical factors might influence user experience. Use cases include regularly validating connectivity between a web app in one region and a database service in another, or verifying that hybrid networks remain stable across on-premises and Azure resources. Through detailed reporting in the Azure portal or customized dashboards, Connection Monitor helps teams respond proactively to emerging issues, reducing the overall risk of prolonged disruption. Network security groups, NSGs, play a pivotal role in filtering inbound and outbound traffic, while user-defined routes, UDRs, fine-tune routing tables to achieve more granular traffic distribution. Despite their usefulness, these elements can complicate troubleshooting when improperly configured. A seemingly minor mismatch in a UDR's next hop can reroute critical traffic away from its intended endpoint, leading to failures or performance bottlenecks. Similarly, a restrictive NSG rule can block administrative protocols or essential backend services that need direct connectivity. When diagnosing a connectivity fault, it is wise to systematically disable or reorder NSG rules and verify whether traffic resumes as expected. Reviewing any manually created routes in parallel ensures that newly assigned next hops align with application design. By methodically working through route tables, analyzing priority levels, and testing security rules, administrators can isolate specific misconfigurations. This measured approach prevents accidental exposure or inadvertent blockages when refining virtual network topologies. DNS resolution is critical to seamless communications in Azure. Once resources have been created with dynamic or static public IP addresses, ensuring correct DNS mapping lets services interact efficiently. Issues often arise when organizations use custom DNS servers that do not have consistent forwarders configured or when DNS suffixes differ from the default Azure structure. Administering DNS zones within Azure or integrating with external DNS providers creates additional layers of complexity. In a troubleshooting scenario, Analyzing DNS records like A or name entries helps confirm that domain names resolve to valid IP addresses. Azure's built-in DNS querying tools can diagnose whether an internal or external domain translates properly. With user-defined routes in place, verifying that DNS traffic is not being redirected away from intended DNS servers is also vital. By systematically checking each step in the lookup chain, administrators tackle resolution failures swiftly without negatively impacting other parts of the environment. For hybrid connectivity, Azure VPN Gateway serves as a critical link between on-premises networks and Azure resources. An operational VPN gateway depends on stable IPsec tunnels, matching shared keys, and accurate routing configurations on both sides. Connectivity interruptions might result from expired certificates, mismatched tunnel configurations, or out-of-sync security policies. When diagnosing issues, verifying Phase 1 and Phase 2 settings can pinpoint which step in the handshake process is failing. Detailed logs, accessible via Azure Monitor, capture handshake attempts and highlight potential negotiation errors. Administrators should also confirm that user-defined routes do not inadvertently send VPN traffic to the wrong interface. Another best practice is to examine the logs from the local VPN device to ensure that both the on-premises and Azure ends correspond properly. By correlating the logs and systematically comparing tunnel parameters, administrators can address not just short-term disconnections, but underlying misconfigurations that risk recurring disruptions. ExpressRoute enables private, high-bandwidth connections between on-premises environments and Azure, bypassing the public internet. While robust and secure, ExpressRoute still demands diligent configuration and monitoring. Common issues include incorrectly set BGP session parameters, incomplete route advertising, or mismatch in VLAN settings. To diagnose these scenarios, commands such as show ERP and show BGP neighbor on the router side can confirm if prefixes are propagating correctly. Additionally, administrators can use Azure's Network Watcher to test connectivity from specific subnets across the ExpressRoute circuit. If traffic fails to traverse the circuit, verifying the circuit's provisioning state within the Azure portal ensures no administrative oversight occurred. In production setups, unexpected route changes or large route tables can degrade performance. Continual checks, employing built-in monitoring or direct queries to the ExpressRoute resource, help validate the network state and retain consistent throughput. Such meticulous oversight guarantees that mission-critical applications consistently benefit from stable private connectivity. Azure load balancers distribute traffic among multiple instances, ensuring high availability and scaling options. However, detecting connectivity failures here requires specialized considerations. One frequent issue lies in stale or misconfigured backend pool entries, causing requests to be sent to decommissioned virtual machines. When traffic distribution fails, verifying health probe configurations becomes essential as the load balancer decides VM availability based on probe responses. Additionally, checking inbound NAT rules helps confirm that the correct ports are open for desired traffic. For instance, an incorrectly specified or overlapped NAT rule might unintentionally block RDP or SSH connections to a VM. By using packet capture and IP flow verify, administrators can trace if the load balancer is dropping packets or if the target is simply not responsive. Monitoring metrics like inbound and outbound flows also helps measure how effectively the load balancer distributes tasks. This systematic approach supports consistent performance while reducing the likelihood of sudden load-related outages. Beyond the individual tools provided by Network Watcher, Azure offers a constellation of services for advanced monitoring. Azure Monitor aggregates logs from various sources, including NSGs, application gateways, and on-premises data centers, enabling correlations across multiple layers of the network. Metrics Explorer helps isolate trends in CPU usage or network throughput, linking them with potential connectivity disruptions. Deploying Azure Monitor alerts can proactively notify administrators if latency surpasses a predetermined threshold or if a specific connection fails repeatedly. Another layer of insight is gained through integrating with application insights, which provides end-to-end transaction monitoring and can reveal bottlenecks at the code level. These advanced capabilities uncover patterns that might not be evident through simple traffic analysis. By aggregating and correlating logs and metrics in a single view, administrators can maintain a real-time understanding of network health and respond rapidly to dynamic infrastructure demands. In complex Azure environments, network troubleshooting often requires evaluating how different services coexist. For example, an application gateway might route HTTP traffic to a web tier, whereas a separate Azure firewall instance filters outbound connections to external APIs. With multiple layers of security and routing, even minor misconfigurations can disrupt workflows. A key practice is to map traffic flows end-to-end across load balancers, security appliances, and user-defined routes to visualize where each packet originates and terminates. Similarly, integrating third-party solutions, such as external firewalls or intrusion detection services, adds new variables that must be tested. Administrators also verify that services like Azure Kubernetes Service or Azure Virtual Desktop do not conflict with existing network rules as they scale. By systematically tracing all segments of the route and comparing them against documented access requirements, organizations can detect hidden dependencies. This integrated view ensures that no single service undermines the network connectivity necessary for performance and reliability.